Good morning. Today's topic, semi-batch reactor. What is a semi-batch reactor? When do we have to select a semi-batch reactor? What are the advantages of semi-batch reactor over the other reactors? This is what we will see, and then go to the actual derivation and how we actually conduct this in the lab. Okay? Yeah. So semi-batch, I'll be taking one example, ozonolysis of dieffluent. Yeah, ozonolysis of dieffluent, what happens in ozonolysis of dieffluent? No? It is the way of degradation of, it's the method of degradation for dyes, okay? And what really happens there is, it's basically a gas-liquid reaction. It's a gas-liquid reaction. And what happens here? No, there will be effluent taken in the batch mode. Effluent will be taken in batch mode. And what is this effluent? This effluent has dyes in it. This is a textile effluent. No? This will be having dyes in it. And a reactant gas will be bubbled here. Reactant gas is bubbled at the bottom. And there is degradation happening with the release of certain gases in that. Carbon dioxide is a main component, which will be further used for fermentation process. Okay, and here after the reaction you have degraded effluent. That is dyes, which the concentration of dyes would have been come down, the chemical structure would have been changed. So it is degraded dye after certain time. Maybe if the reaction is carried out for an hour or 2 hours, it depends. So at the end of the experiment, the requirement is a degraded dye, which can be sent into the water bodies. Okay, safely sent into the water bodies. Okay, so here effluent is in batch mode and reactant is in continuous mode. Such reactors in which one of the reactant is in batch mode and one of the reactant is in continuous mode are called as semi-batch reactors. Are called as semi-batch. I did just spelling mistake here. They are called as semi-batch reactors. Okay, and some more examples. These are very commonly used in polymerization reactions and polymerization industries, where many number of monomers are slowly fed into the reaction vessel. And and very important thing is in multiple reactions you would have already studied what is a desired product and what is an undesired product. And to get the desired product, how the reactors are to be connected. So there also, if the selectivity of the desired product is a very important, of course, it's a very important criteria, the selectivity of product. So for that selectivity, maybe it is required for one of the reactant to be present in excess always. The concentration of one of the reactant should always be in excess. So during those cases wherein the desire for achieving the desired product, if the reactant concentration has to be maintained at a higher level, then also semi-batch will be selected. And other important thing is good temperature control can be obtained in a semi-batch reactor. If the reactions are highly exothermic, then such reactions can be carried out in a semi-batch reactor by altering the flow rate or the concentrations or whatever the procedure, and it can be safely or comfortably carried out in a semi-batch reactor. So selectivity and some temperature control are very, very important advantages of a semi-batch reactor. Okay, so yeah, let me go to the derivation part, a bit of derivation part for this semi-batch reactor before I explain the lab procedure. But for that, you have to know something. Okay, you have to know something. Suppose what am I doing here? I am taking one reactant in the reactor vessel. Okay, one reactant in the reactant vessel, and I'll take that at a certain volume, and I call that as capital V0. Note, capital V0 says volume of the reaction mixture which is initially taken. taken initially. Okay, and let me call that as capital V naught. Now, now another reactant should enter. No, continuously it will be entering, and let this enter at a certain flow rate V naught. V naught. Let me call it as certain V naught liter per hour. And when the first drop enters the content which is already present in the reaction mixture, no, at this I'll start the stopwatch. We have to start the stopwatch. Okay, you start the stopwatch, and at the end of 10th minute, what we will do? Suppose this it has filled till here at 10th minute. At 10th minute, it has come somewhere here. At 10th minute, draw some sample. 10th minute, draw sample and send for analysis of and analyze CA. Analyze CA value. CA naught was initially taken. CA naught, it is CA naught initially when I take this, and at 10th minute, no, 10th minute, draw 10 ml of it and draw the sample and do the analysis for finding out CA value. Okay. So now, what will this total volume be? This is V naught into how much time did I wait? 10 minutes I waited. So let me call that as T. So what will this total volume of the reaction mixture be? It is V naught, the small V naught into T. We call that as capital V, the volume of reaction mixture, capital V, at any time T. So V is what? Volume of reaction mixture, at any time T. At any time T. And this will be capital V naught plus small v naught into T. What is the small v naught? Liter per hour, flow rate, whatever I said. And this T, I waited from V naught till this 10th minute. What is the volume? Okay, and this V naught is initial. Initially, suppose if I had taken 400 ml, this will be 400 ml. Okay, good. So this is one part. So our total volume will be V is always V naught plus V naught into T. Let me note that one in one place. Yeah. Now, for the second reading, I'll wait for 10. See, once the stopwatch is started and this flow rate has started, no, it should run continuously. We are not stopping or decanting anything here. We should run continuously. Okay. So now, at the end, I'll allow the reactants to, I'll wait for 20 minutes more. 10th minute, then 10 minutes more. 10 minutes more if I wait, it will be 20th minute now. At 20th minute, draw the sample and send for analysis to find CA. Okay. And what will the second reading be now? This is at 10th minute. Total volume of reaction mixture at 10th minute. Here I'm finding 10, whatever time gap you give or whatever time you will be setting, no, that will be this T. Okay. So now what will be V20th? This value V 10th minute, that the total volume, this will be my initial volume now, correct? What this initial volume will change, this becomes my initial volume now. We at 10th minute plus V naught into T. And what will be the next reading at 30 minutes? At 30th minute. At 30th minute, it will be V at 20 minutes. Already I have it is filled till here, no? So from here to here. I hope you're getting this. See, for 20th minute, it is whatever till here. This V naught, whatever is here, plus V naught into nu T. Getting? For 20th minute, this plus this is V naught into T. This is V naught into T. So this plus this. So it will be, this is what I can call this as 10th minute. Plus, similarly, V at 30th minute will be V at 20 minutes plus V naught into T. Like that it goes. So hope it's very clear now. What is V, capital V, what is capital V naught and small V naught and T. Okay. Yeah. So now let us go to the derivation. Yeah, let me go with material balance for A first. Material balance for A, material balance for B, and then find out CC and CD. Okay, it's very interesting. Material balance here is very, very interesting. So it also depends on how much you have already understood about the material balance and how you develop the performance equations, how you have developed the performance equation. So let me go with material balance for A. Material balance for A. What did we do? A was taken in the reactor vessel initially, correct? A is already present in the reaction vessel. So let me come back to the material balance equation. Input is equal to output plus disappearance plus accumulation. Accumulation. Okay. Now, A is already present in the reaction vessel. So is there any continuous input for A? No. So that will be B. And am I drawing A continuously out? No. Everything actually is accumulating in the batch. So nothing is drawn out. So 0. And rate of disappearance is minus RA into V, and accumulation is DNA by dt. DNA by dt. Okay. And I know something. What is that? Na is equal to Ca into P. What will be DNA by dt? DNA by dt will be Ca into dV by dt plus V into dCA by dt. Okay. But from this I can find something. What will be dV by dt? dV by dt is equal to V naught only. Differentiate this. So dV by dt will be equal to V naught only. So now I'll replace the Ca into dV by dt as V naught plus dCA by dt. Now this R, let me take this to LHS and it becomes plus RA. RA into V is equal to DNA by dt can be written as Ca into V naught plus V into, I just missed V, plus V into dCA by dt, or RA can be written as Ca into V naught by V plus dCA by dt. Okay, but I'll be consolidating all the equations in one form. So like that, I'll be writing that equation here. Okay, and that equation is dCA by dt is equal to, what is RA? See, minus RA equal to KCACB. And what do I have here? Plus RA. So plus RA will be minus KCACB. Can be written as minus K is equal to minus K CACB minus CA into V naught by V. Okay. And I can also get an expression for K now. K will be minus of dCA by dt plus Ca into V naught by V by CACB. Okay. And how do I find this dCA now? See, during the experiment, I said at the end of 10th minute, 20th minute, 30th minute, what did you do? You pipetted out and sent the solution. I mean, you had analyzed the solution to find the value for Ca. So what do you have now? Ca versus T data. So Ca versus T. What is happening to concentration? It is decreasing. So obviously the nature will be something like this. Okay. So now what you do? You note this. Suppose Ct is equal to 10th, and at 10th minute is some Ca you would have found. So go there, drop a tangent and find the slope, and this slope gives you dCA by dt. So like this you can find dCA by dt for all the readings of T and Ca. Okay. So this is how you can get and CB. CB, how do we find? CB is very simple. CB CB is equal to CB naught into M minus XA. And what is M? M is equal to CB naught by CA naught. And now XA. How do we find XA? XA is very simple. NA naught minus NA by NA naught. This can be written as CA naught into V naught minus CA into V, capital V, note that, very important, CA naught into V naught. This will be your XA. And what is this V? This V is very important. V is equal to V naught plus V naught into T. Very, very important thing during your calculations. Okay. So like this, we have developed some equations for A. Now, let me go with material balance for B. Material balance for B. Will it be same? No, B is continuously coming in, but nothing is going out. Nothing is going out. So think now, what should be input? What should be output? Okay. Yeah. So let's continue. Is there a continuous input for B? Yes, it is there. So let me call it as FB naught. Okay. And is it continuous removal of the products? No. So let it be 0. And disappearance RB into V and accumulation dNB by dt. Very simple. And yeah. So in this FB naught, right. FB naught can be written as CB naught into V naught, which is equal to 0 plus minus RB into V, and dNB can be written as V into dCB by dt plus CB into dV by dt. You know NB is equal to CB into V, and that is how I write this. And 0 plus of minus RB into V plus V into dCB by dt plus CB into V naught. dV by dt is V naught. Okay, yeah. CB naught into V naught. Now we have to write dCB by dt. Okay, so dCB by dt will be equal to dCB by dt will be equal to RB into V. This minus if it comes this side, it will be plus RB into V plus V naught into CB naught minus CB. Let me take this V here first. This will be, yeah, this is your expression. Okay, so let me consolidate that expression here. I'll write it from the beginning. dCA by dt is equal to minus KCA CB minus V naught by V into CA. This is what I had got, right? Hope I'm clear. KCA CB is equal to C into V naught by V. Okay, correct. Now dCB by dt will be RB also can be written as minus RA KCA CB plus V naught by V into CB naught minus CB. This is how we are will be consolidating the equations. And dCC by dt can be written as KCA CB minus V naught by V. V naught by V into CC. And similarly, you can write dCD by dt. CA CB minus V naught by V CD. Okay. So yes, these are the equations used, and in your lab you will be finding this value and this value. So these are the equations for a semi-batch reactor, and in the lab, is it, you will be finding this K value, and XA value. Okay, how we actually do in the lab, what we actually do in the lab. Okay, let me come to that now. Note that yeah. So let me first list out the reactants used. Reactants used are 0.1 normal NaOH and 1 liter of this. You have to prepare 1 liter of this, and 0.15 normal ethyl acetate, and you have to prepare 10 liters of this, and 0.1 normal oxalic acid, OA, 100 ml will be sufficient, and 0.1 normal HCl, and this is also around 200 ml you may need. Okay, so why do I need this oxalic acid? For standardization of NaOH. Standardization. Okay, and this HCl will be standardized with NaOH. Standardized with NaOH after this, after getting the value here. Okay, so these are the reactants required, and now we are ready with the experiment. After standardization of 0.1 normal HCl, no, not 200 ml, you may need more. You prepare around 500 ml. 500 ml of 0.1 normal HCl. Okay? After preparing this, first step is keep this conical flask with 10 ml of 0.1 normal HCl, whatever you have prepared. First step. Okay, this should be ready, and maybe around 10, 20, 30, 40, 50, 60, 6 such conical flasks should be sufficient. Okay, now let us start with the reaction. Reaction is very simple. A batch reactor is selected for this. A batch reactor is one in which there is a reactor vessel and reaction vessel, and a provision is provided for agitation. There is a provision for agitation. Okay, here what I do, I will take 400 ml of whatever NaOH I have prepared. NaOH. It is 0.1 normal requirement, but whatever standard you are getting, you should note the same value here. Okay, so 400, your V naught is 400 ml now. Okay. Now what I do in the overhead tank, since we are not conducting here, once you go and stand near the setup and conduct the experiment, you should be able to do by going through this. In the overhead tank, what do I have? 10 liters of 0.15 normal ethyl acetate. Okay, so now what I'll do, I'll allow this is connected to a rotometer. And the reactants are allowed to flow into the reaction vessel. Okay? So here, this is V naught LPH, which I have to note always. V naught liter per hour. Okay. So now we have filled everything. Don't set the flow rate. It is just we have filled this, and the conical flasks are ready. Okay. Now we will actually start the experiment. Okay, start the stopwatch as soon as the first drop comes here. There is already 400 ml of NaOH, right? So when the first drop comes, start stopwatch. Start stopwatch. Okay, when the first drop comes, start the stopwatch. Okay, and allow the flow rate till 10 minutes. Allow it to flow for 10 minutes. Allow it to flow. Allow this reactant to flow for 10 minutes. Okay, and at the 10th minute, 10th minute, don't stop stopwatch or the flow rate. It should run continuously. Stopwatch also should go continuously and flow, and the flow this also should flow continuously into the reactor. 10th minute, what you're doing? 10th minute, you're just pipetting out 10 ml of this 10 ml of reaction mixture into this conical flask, which already has 10 ml of 0.1 normal HCl. Okay? And titrate this against NaOH. Fine. Yeah. So now, we have not stopped the experiment. Reaction mixture is continuously coming in, and the time also is continuously going on. Okay. So what are we actually doing? T we are noting, and Ca also we are finding after finding the titer value. How to find Ca? I'll show you in the manual. Okay. How to get Ca value from the titer value. Yeah. Next, at the end of 20th minute, now let it flow. So at 20th minute, 20th minute, draw sample and repeat the procedure. Okay. Nowhere you are stopping the stopwatch or the flow rate of ethyl acetate. They should be continuously running. Once you start the experiment, you are not stopping this flow rate or the stopwatch. It should run continuously. But at the interval of every 10 minutes, just draw the sample and send for analysis. Do the analysis. That's it. Okay. So by doing so, you'll be having values for P and C. Okay. So this is how you actually conduct the experiment, and yeah, this is how these are the readings which you will be taking, and this one also, like T into V naught. V naught is fixed. Once I have fixed one, this is continuously one reading continuously, certain LPH. Okay, so rest all is calculation. Okay, let me just share the. One second, I'll just check whether I have opened the sheet. Yeah, let me present it. Oops. I think too many things are open. One second. Yes, let me present it now. Okay, so here you can see now. You can see here. See, after standardization, note down the value for NaOH. And yeah, let me come for finding. Why I'm sharing this is Ca naught and Cb naught. No, they are a bit different here. So we have to see that. We have to observe that. What is that? Okay. Yeah. See here. Ca naught, how do we find? Actually, what is Ca naught? As soon as you start the time, stopwatch, T is equal to 0. Whatever is there in the reaction mixture, that explains Ca naught. That is the Ca naught value. So it is N into V of NaOH by total volume of reaction mixture. See, initially, I have only 400 ml of NaOH. No reactant has come still, though I have started the stopwatch, and though it comes, no, B, whatever enters, if it is compared that ml, milli ml, which is compared with this 400 ml, will be negligible at t is equal to 0. So if I say, and mathematically also, see, if I go with the mathematical equation also, you can see here. So V, capital V will be 400 only. So this total volume of reaction mixture will be still 400 only, though there is a drop of B reactant B. Okay, and this here also total volume of reaction mixtures remains the same, 400 ml. Okay, so that is how you can find CB naught value. And yeah, so here CA is very simple, normality and volume of HCl minus normality into volume of NaOH, which is the titer value. Volume of NaOH run down, the titer value. Okay, so hope I had called that titer value as Y in all the other experiments. Let me call that as Y only. Okay, yes. So yeah, CB, of course, CA, everything is explained. So with this, you should be comfortably completing the calculations. Okay, so yes, hope you have understood this experiment, and when you go near the setup, you should be able to carry out this experiment comfortably. Okay, thank you.